So we're all here to hear about worming our way out of a mess. So let's start at the very beginning. We're going to be talking about the New World Nippostrongylinae. So what the heck is a trichostrongylid? Let's start there. It's a successful group of nematodes. They're considered the most damaging parasitic nematodes of domestic animals. And commonly they're used as a model for hookworm life cycles. But there's an issue with this. Very few have been published, very few investigations have been published on their relationships. So this isn't surprising if you work with nematodes. Nematodes pose a problem for researchers as they are morphologically constrained due to this big old cuticle. If we all go back to when we learned about nematodes, they're tubes inside of tubes. And bigger issue is that most of their diagnostic traits are found in the first anterior third and the last posterior third. And there's a diagnostic bias placed on male worms, which is also an issue. If we think about it, there are less male worms present compared to females, as we don't need as many males to inseminate females. So let's talk about the heligmonellidae. We're going to work down. We're going to do a big funnel down. So they are a globally distributed family of nematodes, and they primarily use rodent, lagomorph, and tragulid and dermopteran hosts. In 1983, by direct to say, they were divided into 4 subfamilies on the basis of morphological characters. So this is the orientation of the synloth. So here we have 2 diagrams. I apologize that they are in French. Here's a synloth. This is made by making a cross-section of the worm. From here, we can look at the synloth and these things called arêtes, or they will be called ridges today. We also look at the presence of a crine. This is just an extension of the cuticle with modified ridges. And we also look at the degree of the division of the dorsal ray. Here are some other examples of synloth that we see within these worms. And here is a bursa. These worms are armed with a copulatory bursa in the males, and we can see division of these rays within the bursa. And we can use those to diagnose different groups. So these guys were diagnosed into the Brevistriatinae, the Heligmonellidae, the Nippostrongylinae, and the Pudicinae. And there's a bursa for you guys, just to show you what this looks like when we spread them out. So now we're going to focus on the New World Nippostrongylinae. That's what we're focusing on here. The New World Nippostrongylinae has no apparent synapomorphy, but they are generally diagnosed based upon the following. So we have the reduction of the buccal cavity right here. The synloth comprised of 4 to 6 cuticular ridges. So we can see that right here. This is what a synloth looks like in real world. Kind of hard to look at. We also focus on a lot of different morphology of this. We are looking to see how many cuticular ridges they have, the axis of orientation, how those ridges are oriented in themselves. We also are looking from where sagittal axis is, which is where these nerve cords are. We're also looking at gradient and size of the present ridges, the dorsal ridge or more numerous. In the males, we're looking at the copulatory bursa and its morphology. The morphology of, here's a copulatory bursa for you guys. We're also looking at the morphology of the copulatory bursa in general and the variation of the genital cone. You can see that there. In females, again, there's less of a diagnostic bias on females in general. So we're looking that females are monodelphic, meaning that they only have one branch to the uterus. So the vulva opens, where is she? Opens right there, and then we can see the uterus coming out through here. There's only one branch. We're also looking that the female lacks a sharp cuticular spine, which we cannot see there. So these guys are distributed through the New World. They are distributed from New Jersey down to the southern cone of South America. And here is the current described genera that we are seeing in this group. But there's problems. Due to the practice of using the same characters to diagnose the different levels of hierarchical levels, there is uncertainty to the diagnosis of the genera within the Nippostrongylinae. What does this mean? Current synapomorphies include the direction and the gradient type of the synloth, so there's no particular specific synapomorphy. So again, no clear synapomorphy. And how can we base our diagnosis of worms if we put the cart before the horse? So that's the root of this problem. And that's my goals is, few investigations on the systematic genera of the Nippostrongylinae, despite their medical and veterinary importance, which is an issue. And the characters are ambiguous and there's no characterization of morphological variability. And this is an example, the Carolinensis, a genus true and dear to my heart. The Carolinensis was originally proposed as a subgenus of Longistriata by Travassos in 1937, based upon the arrangement and pattern of the rays of the copulatory bursa. Again, kind of a general description. And then further taxonomic work led to the splitting of Longistriata into 4 genera. And here we can see Boreostrongylus, Hosselstrongylus, Stylostrongylus, and Vexillata. These are based upon only morphological characters. So here we can see these Synloth cross-sections, and that was a major tool to use to diagnose these worms. So continuing with that problem, 10 of the 13 recognized carolinensis are known from the New World, with C. carolinensis being the type species, and members of these genera were only used morphological tools to diagnose them. These are all carolinensis worms, just to show you the problem that we're seeing. All these bursos are all from things described as carolinensis. Pretty difficult to tell the difference in these tools that we used. So what am I doing in this project? I will present the description of a new species that demonstrates diversity of the group and levels of morphological convergence, provide the first molecular phylogenetic framework to test the validity of the New World Nippostrongylinae as a monophyletic group, and test several characters to identify traits that define nodes within recovered trees using ancestral state reconstruction. Again, these traits are not specific. We need to find clear synapomorphies to elucidate information upon this group, and that is the goal here. So let's begin with the new species. This was incredibly exciting to find and use collections to describe a new species. So in 1997 to 1998, an expedition to Peru from the Smithsonian Institute was conducted, and there they collected mammals. From some of these mammals, from Uriorizoma titis, 3 new nematodes were found from the intestines of these rice rats. So when people think of Peru, they think of a very montane, Andes, high altitude. But people forget that a big portion of the Amazon rainforest is throughout Peru. So here's Kashiriari. This is where these rats were collected. This is where these nematodes are from. It's in the Amazon rainforest. So that's something interesting to consider. Up until now, Nippostrongylus, what we have described a new species in, is monotypic. And these guys, Nippostrongylus bicaudatus is from Adelomys dorsalis, this cute little rat right here, and they're from Argentina. Interesting. What we found was something from Peru.
Keep going.
Okay, so these rats were not collected fresh from me. These rats were requested from a collection. So I did not get to go into the field and go trapping. So these rodents were prepared as food specimens and archived in Peru, in the National Museum in Peru. These carcasses were requested from this collection and subsequently necropsied. Here's the host species, just so you guys get an idea. From here, these nematodes were requested by me from a collection, and they were cleared in glycerin and ethanol mix for observations. If any destructive sampling had to be done, we mounted cross-sections in a glycerin jelly slide for observation. And the observed worms were deposited in the end in the Harold Manter Laboratory in Lincoln, as well as the National Museum in Peru. So here's a female, and here's a male. So we'll start talking about these structures. We did take and look at the female structures, which are going to be pretty interesting to discuss here soon. So we also did scanning electron microscopy with the help of the Image Center at SIU. And from here, these worms went through the standard process to be looked at by SEM. So let's talk about the meat. You guys want to hear about a new species. I came here to tell you about cool things. So again, as I mentioned, most of my characters are going to be in the first third, the first anterior third, and the last posterior third. So looking at it, our new species is over here. This is the current described species. They look pretty similar, right? We got an esophagus, we got a nerve ring, we got an excretory pore, we got this anterior cap. Same over here. They look pretty similar. Here's where things get interesting. Here's the female tail, this weird false structure. Okay. So here we can see, this is the true tail. I like to call it the true tail, because here we have the vulva and the anus. This denotes that this is tail. Here's the post-anal tail. But then we have this structure right here. So it's known as the cuticular caudal appendage. I think of it as a pseudotail. This is just all cuticle. Well, in the Nippostrongylus bicaudatus, we can see it here. Here's that true tail. But the vulva's over here. Well, the vulva in our new species comes out at this junction between the true tail and the caudal appendage. Also, ours is, hang on, ventral. Well, this one is dorsal. So that's interesting. These structures are different. Here are the male. So here is the male of Nippostrongylus, the new species. We can see these spicules. These are the male copulatory organs. Incredibly long, taking up almost half of the species, of the individual itself. while here in A. bicaudatus, they're pretty short. So a practice that we do is called spreading a bursa. These guys look kind of like a mermaid tail when they're spread, right? And they have these rays that look like fingers. But when we see them, they're all bunched up like a rose. So a skill you have to learn when observing these are spreading them. So here we can see in the male bursa of the new species that it has almost a heart shaped with this incredibly long dorsal ray. While over here, we have a pattern of the bursa that's different. This is 4-1, while this is 1-2-1. And here we can see that short dorsal ray. So what does this mean? Oh, no, we got more. So here are these cross sections, these synmoths, what are used to diagnose different genera and species of these worms. Here we can see they're pretty similar. We still have that gradient that they are described as having. They have a gradient going through the synmoth. And they are about the correct degree delineation from sagittal axis. And then we have the SEM images of the female tail. Here we're going to look at it a little bit more. So again, there's that true tail with the vulva and anus is up there. And then we have that caudal cuticular appendage. And that vulva is coming out at the junction between. Well, here in a light microscopy, we can see there's the vulva. So this is kind of reinforcing that these worms are different. So based upon 25 worms from 3 individual hosts, we describe this as a new species. And you're probably going, Gwen, they're different. Why did you put them in the same genera? Well, we as systematists have to remember to propose the most conservative new species. Each species description is a hypothesis. So rather than create new genera, because what's the point of monotypic genera and monotypic genus, when this new worm fits the characters of a Nippostrongylus to the best that we know of. So we included it in Nippostrongylus. So let's get into the meat and the bones of this presentation, the actual phylogenetic estimation of the New World Nippostrongylinae. So we've talked about this already. Nippostrongylinae has a super troubled taxonomic history. Many species were described from singular host localities, singular specimens, and singular hosts themselves, and they're limited. We don't have a lot of them. And there's a tendency to use the same characters to diagnose different hierarchical levels, which is an issue. We're putting the cart before the horse. And these characters used to define the subfamily are technically intensive. They often require destructive sampling. Making these cross sections, I have to cut up a worm. So, and to date, there's no clear synapomorphy. There are suggested synapomorphies, but nothing that delineates that this is the synapomorphy. So we need to create a robust molecular phylogeny that's going to create a framework, map characters, and predict new characters. That's the goal. We need to create an actual framework. Until now, we've had this box that previous researchers have suggested different characters. Now we need to go in and test these ideas, this box, to test new characters and new technologies to help create a better framework. So to achieve this, we are using 28 nematode genera, 8 belonging to the Nippostrongylinae, with a total of 85 nematode sequences, 31 sequences belonging to the Nippostrongylinae, and the goal was to have at least 2 species representative per genera, so that we had a strong phylogenetic signal and we can test that if these proposed genera are actually monophyletic. So here were the taxa used. Those highlighted in yellow are all in our in-group. So the current diagnostic characters for the Nippostrongylinae are limited and vague. I keep reiterating this. It is important that we acknowledge that we need to find new characters and test those that we are using. And having a robust molecular phylogeny and applying an ancestral state reconstruction will test the monophyly of the Nippostrongylinae, test the validity of proposed characters of the Nippostrongylinae, observe the relationship and relative position of resulting clades within the phylogeny, find synapomorphies that define the subfamily and resulting clades, and provide a framework to test the validity of characters within the ancestral state reconstruction. So how did I do this? I did not get to go in the field. All of these are used from collections. All specimens used came from collections and were loaned to me. So that was pretty cool. And a lot of these worms came from trips from South America, Mexico, United States, and they were identified and accessioned into a collection. Then if we couldn't get any genera that we needed to see, we used GenBank, and we downloaded sequence data from GenBank. So we had to do observations to identify these worms. So I looked at reproductive genital structures and cross sections that were made to diagnose and look at diagnostic structures. And then worms are assigned a field identification to the genus level. So here are some worms to look at. From here, after those observations were made, we took the same worms that observations were made, and we cut them into thirds. This allowed me to take a molecular sample, and also have a physical voucher to identify worms. So I got the same molecular sequence from the same worm, which is cool. So what we do is take the anterior end, posterior end, look at those under a microscope and diagnose. This no man's land in the center, because again, most of those diagnostic characters are found here and here, we can use that to take a molecular sample. So from here, I sequenced three genes, 28S, internal transcribe spacer, ITS, and cytochrome C oxidase, CO1. These sequences were assembled in Sequenture or Genius Prime. Then we imported these into Mesquite, and ITS and 28S, we used a secondary structure alignment program called Kinsey, which is within math, and CO1 was just aligned using muscle. We then used IQ-tree to produce maximum likelihood, so bootstrap, phylogenies, and then Mr. Bayes for Bayesian inference, which is giving us posterior probability. So here are my primers I used. I have 28S, ITS, and then I used 2 sets of primers for CO1. Of these 3 are nematode specific, while this is a universal primer. So let's get into the trees. That's why you're all here to see this, right? You're ready to see some trees? All right, so here's our 28S maximum likelihood tree. On here, we have both the maximum likelihood and the bootstrap score. So here is the Nippostrongylinae, which is Haligmanellidae, and Nippostrongylinae is representing the family Haligmanellidae. And here we can see that Carolinensis, Vexillata are paraphyletic. That's okay. We're testing this. We're testing, the cart was put before the horse. People had these characters and we're testing it. It's okay that they're paraphyletic, and I'm happy with that. So we can see that there's that. We are also seeing a slight geographic distribution. So here are my Australian worms, followed by worms from Canada and North America. These are from Carbondale, actually. Here we have worms from Mexico and Arkansas, followed by South American worms found in this clade, this Malvanema Hosselstrongylus Guerrero-strongylus clade, and then worms from Mexico. In the ITS tree, we're seeing, again, a similar trend. We are seeing that Carolinensis, Vexillata, and Hosselstrongylus are paraphyletic. And again, we're seeing this slight geographic distribution. We're seeing that like Carolinensis we have Carolinensis from Old World with Menudis, Nippostrongylus from Australia, North America, so this is, Canada and the Midwest. We are seeing Mexican Vexillata here with the Mexican Carolinensis Perez Ponce de Leon. We're seeing Midwest and South American Hosselstrongylus. So that's pretty interesting that we're seeing this distribution overall. And then we also have our Hosselstrongylus up here from North America and from Mexico. So that's pretty interesting. We're seeing this distribution of a breakdown. Again, here's our CO1. I like to call this my problem child because the bootstrap scores were low and the Bayesian inference found a huge polytomy. That's okay. And again, we're seeing the same trend that Carolinensis is still paraphyletic, so is Hosselstrongylus, and it's breaking down into a South American Hosselstrongylus, and other North American and Mexican Hosselstrongylus are kind of floating around the tree. Now the positions, they have changed as compared to the 28S and the ITS, but that's okay. We're okay with that because CO1 is a mitochondrial gene and it's going to act a little bit different. Next, we have our concatenated tree. So this is 28S, ITS, and CO1 all put together. And we did both Bayesian and maximum likelihood inference on this. And what we found is the same trend, is that Carolinensis is paraphyletic, Hosselstrongylus is paraphyletic, Vexillata, and interestingly, we can still see that kind of geographic distribution. Here's our worms from Australia. Here's Carolinensis from North America and Canada. Here from Vexillata from the Midwest. Carolinensis from Mexico and the United States, again from Mexico. So it's still following that trend. Here are the Hosselstrongylus from South America versus Hosselstrongylus from Mexico and the United States. So what does this mean? Well, the Nippostrongylinae are monophyletic. Our trees are suggesting and showing that Nippostrongylinae overall of what we sampled is monophyletic. But there is some variance in the recovered clades. 28S has 4 well-supported clades as compared to ITS that has 5, and then CO1 had the lowest clade support of all data sets. This is probably due to low saturation among codon positions. CO1 is known as a mitochondrial gene, so it's going to have the highest variation of all of them. It is maternally passed on, and it's going to have very high variation, especially in that 3rd codon position, as compared to 28S and ITS, which are nuclear genes, which are going to be a lot more conserved overall. But the recovered phylogeny suggests further investigation into the carolinensis, Guinevere, Hossel, and Vexillata. That those are paraphyletic, and we need to look into how can we resolve that. The concatenated tree was the best overall of maximum likelihood in Bayesian node support, and this can be due to a greater total amount of data. We are observing more base pairs overall. But I'd also suggest that due to those high support values, node support, we're seeing a lack of strong conflicts among the represented genes. So that's good too. There is a concordant signal among all data sets. So we're pretty happy with that. 5 clades are represented in the in group, and there's a concordant signal with the single loci trees. But you might be bringing up, well, Gwen, looks pretty similar to the 28S. Could it be that 28S is a huge gene and might be swamping out data? And that's true. That is a fear that we could be having. 28S is on average about 3,500 base pairs. That's a lot of data, but it's unlikely given the overall higher support values seen within the node support. So what do we do now? Well, I need to test those characters, right? And I have this beautiful concatenated tree on which to test character validity. So once the concatenated phylogeny was recovered, characters need to be evaluated using an ancestral state reconstruction. So what is that? Ancestral state reconstruction evaluates character data in our current taxa, and then it estimates the character states for recent and deep time ancestors within our tree. So this test is going to evaluate homoplasy within current diagnostic characters, evaluate validity of the newly observed characters, and identify synapomorphies for the subfamily and its resulting clades. Oh wait, I need to use that. So we use the concatenated phylogeny as a framework for this test, with 13 characters were being analyzed. 12 of those were analyzed using a categorical, either present or absence. There's options using the MK1 model in Mesquite, and then 1 continuous character, so it has many states, analyzed with a parsimony value and a parsimony analysis in Mesquite. 9 nodes were selected to reconstruct character states. So what happened was we went through, once we got these maximum likelihood scores back, we decided our maximum likelihood cutoff to say a character is diagnostic is 80%. So here are the characters we are looking at. So this is a big list, I understand. So you might notice that we have these in yellow. These are newly proposed characters. You might notice that most of them are female. Again, many of the characters that we have been proposed to diagnose this group are male. There's a diagnostic bias to use male characters because they are easier or more prevalent to score. So these are all female characters except for the distal end of the spicules, and then the rest of these characters are traditional characters, characters that we have used to traditionally diagnose and to describe this group. So here we can see the different states of the Synloth. Here are some of our interesting ones. So we have the expansion of the cuticle found on the female, this sheath that kept showing up and was thought to be an artifact of preservation. So we decided to look at that. We have the bursa being symmetrical or dissymmetrical. And then the interesting one, this spine on the female tail. So we have the button type spine, which is found in the Helicobacter moides, the blunt type spine, which is found in my in group, and then this spike, hair-like spike. So we need to make sure that this ancestral state reconstruction is accurate and is actually accurately predicting what characters are working, right? So to do that, we had a bunch of worms that were kind of difficult to diagnose. It was hard to put them either in one genus or the other, right? So what we did is we went through, I tried to score as many of the characters that these worms had, and then entered them to my matrix in Mesquite. And then the characters that were unavailable were verified using previously documented observations. And then what we were hoping is that the genus level could be provided for these worms that were difficult to analyze. These worms have been coming from collections, so I get them in a state that could be beautiful, absolutely perfect, and I get them in states that they could be not as desirable, a little bit harder to work with. So, based upon the results of the position of the worms within the recovered phylogenies, I was able to provide a genus diagnosis, and then also supported character data from the ancestral reconstruction could help me predict what characters I'm going to see in these worms. So here's the first one. Here's our likelihood analysis. So this is for the first 12 characters, and we're focusing on the spine of the female tail. If you notice, black dot, black dot, black dot, all these black dots, looks like this might be a synapomorphy for this group, as it is in our 9 major clades. Next, we have the gradient type of 0. So this is just a gradient type from big to small, a consistent gradient type, and it looks like it is used as a diagnostic tool within my carolinensis from North America, and then these Australian distributions. That's pretty cool. I like how it's supporting that. Next, we have gradient type 1, which is all over the place. It's not a consistent gradient type. We're finding that diagnostic in the Mexican Carolinensis Ponce de Leon and the Vexillata. All right, that's pretty cool for me. And then gradient type 2, which is consistent ridges across the synloth, is found in these South American worms. It can be used in these South American worms as a diagnostic tool. And then next we have the crane absent versus crane present. Crane present is only found in this group up here, these Mexican distribution, Mexican Carolinensis and Vexillata. And then the crane absent seem to be present in the rest of the worms and can be used to diagnose clades within the rest of the worms. So that's pretty exciting. And then next we have the cuticular enlargement of the female tail. And if you look, you can see that it can be used to diagnose these worms here. And because we didn't have a score for this one, because I didn't have I didn't actually get to see the female of this one, caused an issue and it couldn't be diagnosed in here. Next we have the parsimony analysis, which is looking at how many ridges are found on the synloth. So that is a typical diagnostic tool that is used. You can score these guys to genus using how many ridges do they got. Well, we found out this is all over the place. This is pretty homoplastic. Carolinensis is typically described as having about 12 ridges. Well, Carolinensis here has 12 ridges. Hossostrongylus has 12 ridges. Carolinensis up here has 12 ridges. There's no consistency at all throughout all of this. So pretty homoplastic. Not a great tool for having to organize these worms. So what does this mean? The synapomorphy is the blunt type's female spike on the tail. That's pretty exciting. We found a new synapomorphy and it's a female one. That's pretty cool in my book. And many characters evaluated are homoplastic. The number of ridges on the synloth. Not as inferential as we thought. So what does this mean? Well, fresh collections and better maintained specimens could have solved many of the problems seen in the study. I didn't get to go do sexy expeditions in South America. We attempted some field work and I got flash flooded out of my field site. So what does it mean? It's imperative that we have the proper training in the creation, curation, storage, maintenance of vouchered material is taught. We all need to be responsible. When we go out into the field and we bring back specimens, we have to realize there's so much data that you are bringing back that we need to use these repositories for future science, especially as the world biodiversity crisis, it's becoming harder and harder to get out into the field and do what we love. And look how much cool things I found just using collections. I found a new species, I found new characters, I found a lot of cool work. So I feel like students and researchers need to be less scared of going back into collections and doing the hard work behind closed doors. And you know what? We need to train taxonomy. We need to really work on learning how to train new taxonomists because the loss of natural history collections is hastened by the loss of that skill. So, this was the first molecular phylogenetic framework for the New World Nippostrongylinae. That's pretty cool. I think that's pretty cool. It's a big achievement. We finally got a framework. It's the first piece of this big jigsaw puzzle. And we found that the Nippostrongylinae is monophyletic, and the blunt type spike on the female tail is a synapomorphy, a female character, a group that is not typically used to diagnose new species. That's pretty cool to me. And we also found that many of these clades recovered in the phylogenies are paraphyletic. And further investigation into the following, carolinensis, vexillata, Hasselstrungus, and malvinema, we need to be looking into that. There's something going on there, and how they are proposed now is not correct. So we need to resolve that. And this ancestral stain analysis found that many characters are homoplastic. And we need to, due to those being homoplastic, it further emphasizes the need to look into these worms overall. So that leads me to those who I need to thank and have been incredibly helpful for me. I'd like to thank my advisors in my committee, Dr. Agustin Jimenez, Frank Anderson, and Kurt Newbig, for the guidance and instruction in both academic and personal life. I need to thank all the people who collected these worms and got to do the sexy field work. I need to thank the Harold Manter Laboratory of Parasitology, so shout out Scott and Gabor for helping me out and their students. To Vasil Tkach and students, Mike Kinsella and Dr. Jorge Falcon. I need to thank my funding from SIU and the superb scholars that allowed me to work in meddling collections, which is my favorite thing. Advisors past and present, so thank you to all of those who have helped me, and my peers and cohort members. I don't need to name y'all, you know who you are, and I'm very thankful that y'all were here to help me. And I need to thank my dad. He sadly passed during this investigation, and the new species is named after him. And I'd like to thank him for his support and allow me to be as tenacious as I possibly am. Any questions?